Welcome to a new test and teardown video. This time it's another IMPO electronic, a power supply. This power supply is very, very big. I mean, look at my hand here. The width is more than 40 centimeters, and it is definitely a two-hand lift. So even if you grab here with two hands, you can just barely lift this thing off the table. And it is clearly designed to be hot somewhere inside, right? Look at all those air ventilation holes. It also looks a little bit like kind of homebrew level of manufacturing. If you look here, we see all the lines and markings for all the manual marked holes, and then drilled all the holes by hand and all that kind of stuff. And this is typical IMPO, by the way. I would expect us to find a label inside with a manufacturing year. My guess is 1970. Let's see if I'm right. The fun thing about this power supply is, I guess this will be mains power on off, and again, no indication what is on and off. 2 amp fuse for this AC, fixed AC output. No fuse for that output. No fuse for that output. No fuse for that output. So I guess this is a 0 to 300 volts output, 0.1 amp, and then there is a 0.1 amp fuse up here. So that should be like that, right? And again, a 0 to 24 volt output, 10 amps. Oh. And again, no fuse for that. So this is regulated by PNP transistors, I guess. And this is regulated by a valve. That is interesting to see what is inside this unit. And I would guess this is the meter switch. So now it's standing like this, so you can see the two top handles. And I mean, even with those really good solid, it's a tough job to move this thing around. I really like when units can stand on the front handles without breaking meters, knobs, switches, or anything like that. That is a good way to protect stuff. So that is a thumbs up for that. The rear panel here is also looking a little bit like homebrew. Tons of airflow. Great, great. And then, look what they're doing here. We got a lot of big, bad PNP transistors in here, separated with big distance. And then you can't touch them, so they just put this, but I mean, you can easily touch them right there, like that, right? So that's probably only 24 volts or something like that, right? And that is the little thin, little flimsy-pimsy cable for this power supply. Really? So with the cover removed, we can now get access to the rear-mounted PNP transistors, 2N443, and if we look at the data sheet, it's 50 volts, 150 watts peak, and 15 amps each. Let's look at the power D rating curve. So the 150 watts per unit, that is, of course, ice cold and for a very short period of time. But when you heat this up, you're going to see the hotter the device gets, less and less power you can dissipate, right? And I wouldn't call this a very, very effective heat sink. There isn't really a lot of surface area. There isn't a good coupling to the surrounding air. So that's probably why they're putting in 4 of these in parallel. And I guess this is the 24 volts DC output. Let's have a look. So this is the nice internal view of this IMPO power supply. Just like I assumed, all 4 power transistors, they're running in parallel. We got individual feedback resistors, and I think what we got down here is probably a driver, and this is a pot meter for the output voltage you set using this dial. That is of course for AC output, but I would also expect this to be like a pre-regulation or like an input voltage to the output series regulator. So that means if you adjust for a very low output voltage, you also have a little bit higher voltage, but you have a much lower voltage on your input side of your transistor. So that means you're not dissipating a lot of heat. So that looks, I guess this is what they've done, as far as I can tell. And got a little bit of current sense here. We got diode. We got rectifier diodes down there. I would assume they are connected to the output as well here. Then we rectify that, and then we go to the capacitor. We got some more rectifier diodes over here. I don't know exactly how they are coupled or they are in parallel, right? Because, oh yeah, haha, the wires go down here and then they go up here and here again. Interesting. 2 capacitors in parallel with flimsy thin wires. PCBs like Veroboard. And also down here there's a little Veroboard construction. This one is actually quite interesting. See, AC output goes through a current transformer, current sense, and then output current goes via a relay to that output, for example, right? And then I guess there is a transistor down there, diode, pot meter, and a capacitor. So I would expect this to charge a timing constant. Transistor is driving a relay. So that means if you are pulling too much current, the relay is gonna go chuck, 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 or something like that. This is a typical way to do that. Back in the 70s, then you could easily hear you're overloading something. Probably high voltage discharge here, so there's, what is that? What exactly is that doing? It looks like it's connected to that. I don't know. That's interesting. That PCB down there, by the way, is not a Veroboard. I don't know if we can see this. Let me get a little bit of light in here. It says IMPO type MS on the PCB. It's not the most beautiful PCB layout ever. But again, this is from 1970 or something like that, right? And it's quite experimental with all sorts of modifications. It's not all of these funny modifications IMPO did. I would expect somebody else. They were playing a little bit around. Look at the isolation distance to metal here. Uy, 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 uy. So this is the high voltage output, and I think this is just my first guess. There's no regulation, only rectification. So there's a rectifier. I don't know, where the heck is that? Yeah, look at that. So that black wire is connected to exactly that capacitor with the high value for discharge. But then where do we find the diodes? High voltage diodes. I need to keep looking a little bit. But it's quite beautiful design, a little bit untraditional wires like that. This is mains input, and there isn't any mains input fuse. This is mains input directly to the switch and directly to the mains transformer, and then there's obviously a low voltage output from this mains transformer that goes to the variable transformer here. That is some heavy duty, huh? So this is when you crank up the voltage, you can get directly input output together here, right? And then you go down to 0, and then there's a winding here. There's 0, and then they made another manual stop here. So this is probably 0. Isn't that just cute? I heard this one should work. I think we should power it up and see if it actually works. At least I know for sure there's no explosions or anything, because Frank, who gave me this one, already powered it up. So it's not going to be super exciting for me. We're not going to blow anything up. So let's try and see how much this works. I mean, I really like the powerful lamps here in the meter. So you can see from big distance, this thing is powered on and it's potentially dangerous. Voltmeter is now AC, 24 volt AC output. So this is where I put my meter in AC voltage. Let's look both at that meter and that meter, right? Look at that. It's not bad at all. Ooh, here's a little bit of stickiness. That is actually the meter that is sticky. So let's try and see. Yeah, that is a sticky meter. And then we can crank it all the way to 27 almost. Yeah, so that AC output is definitely working. Let's try the next one. Is there a connection to that one? Okay, some of these outputs, they share the same common. So this is a 6 volts. Let me crank this to 10. And let's try and move that one to that one. 0. Okay, so this one and that one is the same. And between these two is also 10. Haha. And 4. Oh, great. How about that one? So that's an AC output as well. Oh, great. So this 6 volt and that 12 volt, they're actually in series. If you look at the voltmeter here, right? So this one is, yeah, common. And then we go 6 volt here, 12 volt here. But between these two, 6 volt again. Brilliant. And then there's another 6 volt over here. Oi, 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 oi. 32 volts between these two. 25 here. 28. And then between them, 7 volts. So there is a little bit of funny things about grounding here or sharing. You should be careful about this. Look at that. I mean, that's 30 volts. Oh, so this is the unregulated. And then 36 between these two. It could have been smart if they added warnings or indications about that, because this is a good way you can screw up stuff if these goes to the same unit. There could easily be a something in between. They should definitely be floating, but they are not at all. This is a potential user problem, a user fault. This is going to happen, definitely. So let's play a little bit with the DC output. Start the meter to 300. So this is the high voltage output. And definitely that also works. There's a very big capacitor you charge with the DC voltage. So look what happens. You can see here on the meter. This is how slow it goes. And while we're discharging it, I think that was super lucky. Now we didn't get the sticky meter problem. It's here in the middle, so let's try and go up again and see. Ooh, I think I fixed it. I've just been doing this. Yeah, oh, it's back. And then, oh. So there's a mechanical problem in the meter. But that output here is definitely working as well. But be very careful about this. Let me adjust this to 200. Here's my other idea. If I keep this in the ground here and let me try and move my voltmeter to that point. We got AC. 17 volts of AC between these two. Aha, this is a DC. Yeah, okay. So crank the meter to DC mode. To the DC. Is that 20? And meters are absolutely accurate. And 24. I mean, so it seems to be working. I really would like to connect a load and see how well is this regulated. Is there any ripple, or is it regulated, correctly? So how much is the voltage changing when I add load? So let's try this variable regulated 24 volt output. And this is unloaded. I said, why is this light so annoying like that? Okay, so I set the voltage to 19.9 and this is zero load. Now I'm going to load it with 2 amps. Look at that. 0 amps, 2 amps. Okay, let's try and crank up the fun factor a little bit. Let's just go to 4 amps. 4 amps, 0 amps. 4 amps, 0 amps. So that output is definitely regulated, and it's actually working really good. That is great. Now I would like to perform a little fun test. I think I will load this for a little while, and then I will measure the temperature on all 4 transistors to see if they all heat up equally. That will prove if all output transistors are sharing the power. Now I am ready to do the temperature test. I will just set the current down to 2 amps. So that is only 40 watts of output power. And look at that. That's the output transistors, all 4 of them. Yoo-hoo. And are they getting any hot? But I think the most important is they are all exactly the same. Why is this light so annoying? I think I will inspect a little bit more inside. So when you want to use a thermal camera to check temperatures, and especially temperature differences, obviously this is a very shiny surface. So you're really not measuring the temperature of this plate, but you're measuring the temperature of anything else in the room that shines its temperature to this shiny surface. So this is why I always paint stuff with a matte paint like this, and then my thermal camera really works. And now what I can do here is, oops, I can check the temperature of the transistor to be 35, and then the plate right next to it to be 31. So that means there's a very good thermal connection. Obviously it's going to shine a little bit more red like this because the thermal camera like this got auto scaling, so it's going to magnify a temperature difference. So it's always looking like it is a huge temperature difference, but it's definitely not the case. Look at the values and then you're not going to be confused. It's only a few degrees difference between the metal and the transistor, and I got 40 watts of output power and nothing is hot. I mean, you can touch anything here. So that is really not a stupid design with this pre-regulation. That was smart. So let's try playing a little bit with the 300 volt DC output. Let's just crank the voltage up to, I don't know, 200, like that, right? So let's load a little bit. Okay, enable load. Okay, so then the voltage drops a lot. It was supposed to handle 100 milliamps, 50 milliamps. Look at that, the voltage drops quite a lot, and this is only 8 watts of power. It's not really a lot. You can easily see it on the meter here. So well, that's how this output is not regulated in any way. They probably thought that it was supposed to be regulated, or maybe this, I don't know what that really means. There's definitely a PNP transistor here, and this output is regulated by a PNP transistor, so maybe it was at one time regulated by some valves and stuff, but all that is removed, and it is definitely not a regulated voltage. You can also just crank the voltage all the way up to 300, or how about, yeah, okay, like that, right? And then so that is what it is. Voltage is not regulated, but it was a lot of fun to play with this power supply. Only one final word to say is sticky meter. Be careful about the meter, and also be very careful about isolation or lack of isolation between the different outputs. Always be sure that your system can handle that when you use this power supply, because that is clearly a very potential problem waiting to cause some sort of an accident. Discharge time is huge. Did not find the classic IMPO labels about age. I was expecting to find that. So I will just stick to my 1970 something kind of guess, unless somebody will tell me anything better than that. What is written here on this? Oh, handwriting. Maybe we can find. I will continue to search a little bit.